Okay. Okay, I'm assuming you can hear me, Krishna?
Yes.
Okay. All right. Welcome, everybody. Great to have you folks join us today for our first virtual TiE Talk this year, featuring Dr. Vint Cerf. Thank you, Dr. Cerf, for joining us today and giving us your time. We are really looking forward to this keynote speech. And I will also quickly introduce Krishna Pendyala, who will then introduce more formally Dr. Cerf today. So Krishna is our moderator today for the TiE Talk. Krishna is a friend and also a TiE charter member. He's a Vista speaker. He's also the Chief Empowerment Officer at Choice Ladder Institute, which he founded, and also the co-founder of Mindful Nation, and he was also the president of Mindful Nation. He's also an author of a book called Beyond the Pig and the Ape, which is a very interesting book. I have read his book. I really liked it, and I recommend you read it as well. So with that, I want to quickly thank our sponsors, gold sponsor SWOT Capital and Benchmark, silver sponsors Cohen and Company and the Payroll Shop, and Ference Associates are our bronze sponsors, and the academia sponsors are Duquesne University. So thank you for sponsoring us. Without you, we will not be able to do events like this, high quality events, and everything else that we do. So thank you again. And with that, Krishna, I will turn it over to you.
Thank you, Prashant. So this is an incredible privilege for me to work with people like Dr. Cerf. And when I called him doctor, he said, you can call me Vint. And then I got comfortable and I said, can I be informal with your introduction? And he said, absolutely. So the first time Prashant asked me, we're going to have a father of the internet speak to us. I said, is that Al Gore? And he said, no. So I went and Googled, and sure enough, for those of you who want to know more formal introduction of Dr. Cerf, you can go check out Wikipedia and so on. But I have not come across a person who has more back-to-back meetings than him. And therefore, I want to give him as much time, and we're very grateful and honored to have him present to us. So with that, Dr. Cerf, we are very keen to hear, and I loved your title, The Lessons You Learned from the Internet. And when I asked him about 2 pearls of wisdom and asked him whether he would have many more and it would be difficult to choose, he said yes, but he got to 2 in less than a minute. So I'm all ears, and we're all ears wanting to hear your message. Welcome. Let me unmute you.
There, how's that? That should work. So can I get confirmation that you can hear me?
Yes, sir.
Okay, thank you very much. Well, I appreciate the opportunity to join you today. I have a lot of respect for what TiE is trying to do. And I thought I would try to link together some of my experiences with the internet's evolution and the purposes for which TiE was formed. I do have to tell you, though, about the Al Gore side of things. Al is a friend, and indeed, he had a role to play in the internet's evolution. Way back in 1986, when he was still a senator, my partner, Bob Kahn, was asked to testify at one of Al's hearings while he was senator. And the hearing was on networking and computer communications and things like that. And at the end of the meeting, Bob Kahn had introduced the notion of information infrastructure, which included not only the networking aspect, but the computational aspect of information processing. And Al Gore asked the question whether it would be useful to connect all the universities in the US, with the 5 supercomputer centers that the National Science Foundation was in the process of building. And I think he thought of that as an information superhighway, like his father's legislation in the US in the 1950s led to the interstate highway system, which ironically was a Defense Department act, because the idea was to build this interstate highway system and then use it to drag missiles around to keep the Russians from targeting fixed silos. Ironically, I don't think we ever used the interstate highway system for that. We built fixed silo missile systems anyway, but it was the Defense Department that paid for the initial interstate highway program. And so Al Gore saw this as an information superhighway. And indeed, later, as vice president, he helped again to, there was legislation, by the way, that came out of this. It was called the National Research and Education Network Act, and it led to the NSF-Net backbone. Meanwhile, later on, when it came time to make the internet commercially available, then Vice President Al Gore helped with legislation that allowed the government-sponsored backbones, which included the original ARPANET, the NSF-Net, the NASA Science Internet, and the Energy Sciences Network, to carry commercial traffic so that commercial services could be reached by people who were on those research networks. And it was Vice President Gore who helped to encourage that legislation. So we owe Al a lot for his policy side contributions. So let me come back to lessons again. I'm sure many of you are well aware that the origins of the internet started with another program in the late 1960s that was called the Advanced Research Projects Agency Network, or ARPANET. This was built primarily to do resource sharing among the dozen or so universities which at the time were doing research in artificial intelligence and computer science. And the Defense Department, DARPA in particular, said that we can't afford to buy a new computer for every university every year. But what we can do is build a network and let you share all of your resources. And oh, by the way, we will fund all of you. So don't hide your results. Share your results so that we can accelerate the rate at which we have learned or understood artificial intelligence and computer science. So this was an information sharing and resource sharing initiative, and it worked very, very well. The network covered the US and eventually made its way over to Europe by satellite. And we had colleagues in England and in Germany and Italy, Norway, helping us to develop the networking technologies. So the ARPANET was very successful, and in the early 1970s, Bob Kahn moved from Bolt, Beranek, and Newman, where he had been integral to the design and construction of the ARPANET, to the Advanced Research Projects Agency. And the Defense Department, seeing the success of ARPANET, asked the question, is it possible to use computers for command and control? Could we augment our human planning capability, our ability to keep track of our resources, especially in in a battlefield situation? Could we use the computing power to make more effective use of the resources we have at hand? And the thought was that if we really wanted to achieve that objective, we would have to put computers in mobile vehicles and in ships at sea and in aircraft. But the ARPANET had only been designed and built to hold I'm seeing something on the screen saying some kind of an error message here. Oh, no, it just says who's talking. All right. Sorry, I thought it was getting a secret signal. Anyway, the point here is that we built the ARPANET out of dedicated telephone circuits connecting the packet switches to each other. And you couldn't use wires to connect mobile vehicles and aircrafts and ships at sea. And so we had to use satellite and mobile radio. So we had to build a packet radio system and a packet satellite system in addition to the ARPANET in order to test the idea that computers could be used in command and control. which led to the problem of interconnecting these different kinds of packet switch nets to each other, and that, of course, led to the internet problem. So Bob Kahn and I at Stanford University in the spring of '73 were beginning to talk about, okay, so how would you link together these different kinds of packet switch networks of running at different speeds, different packet sizes, different error rates, different latencies, and somehow make them all look uniform. And of course, that's eventually what the TCP/IP protocols did. So the first lesson to take out of this is that it's much easier to tackle a problem when there's somebody willing to write a check to actually have you go and investigate, as opposed to doing a startup, which I suspect a number of you either are doing or have done or have experienced. That's much harder because the venture world is somewhat less willing to take risk than some of the government research agencies, because they have a continuous source of income called taxes, whereas venture capital has a finite amount of resource called capital. So lesson number one, if you're trying to do something that's risky and uncertain, then it's good to find somebody that has a substantial amount of resource and willingness to support the exploration for a long period of time. So just to give you an example, the original ARPANET units were delivered in September of 1969 and a few months thereafter. And the Advanced Research Projects Agency continued to invest in networking research and technology development until 1990. They did other things as well, but the ARPANET was shut down in 1990. That's 21 years. The National Science Foundation started investigating computer communications and networking, first to support the computer science community and then to support all the scientific disciplines, starting in 1982, and they have not stopped. So we're now talking nearly 40 years of continuous investment in various aspects of computer communication and applications. So the willingness to make these kinds of long-term investments usually is only possible to government agencies that are not impatient about getting results. And I would say that it was a real experience to go from being on the begging side of all this, please, sir, may I have some more support for my research, to moving to ARPA, where I was a program manager running the internet program starting in 1976. So suddenly I was the one writing the checks. And I can tell you lesson number two is that it's much more fun to be able to say yes and write a check than it is to be on the other side begging. And so I've learned to appreciate the willingness of people who are in a position to underwrite the cost of research to do so in a, let's say, a persistent long-term way. And so that's lesson number two. Lesson number three comes out directly out of the internet design itself. When Bob Kahn and I started this work, we made some assumptions, and in a sense, those assumptions have served us well all the way up to the present day. One of those assumptions was that of the networks that we were interconnecting, we assumed that we could not change those networks to make them know that they were part of the internet. They'd already been built. They'd already had all their details worked out, but they had different packet sizes and a variety of different parameters. And so when we realized that we couldn't change those networks to know that they were part of the internet, it almost induced the design, because we had to put a box between each network that did know that it was part of the internet. And it used each of the networks simply as a delivery mechanism for internet packets that had been slipped into a local packet format. Think of it as a postcard going into an envelope. And so the gateways between the networks, we didn't know they were supposed to be called routers, so we call them gateways. The gateways between the networks would pull a postcard out of one network and look at it. It would see an internet packet, Then it would figure out where it needed to go in the next network, and then it would write an envelope in that next network's format, put the internet packet into that envelope, and send it on its way. And it would hop through the various networks until it finally got to the last one, and then the final envelope was addressed to the host that needed to receive the data. So it's a very simple concept. And the idea here was to not have too much state information in the gateways, for example. So if a gateway went away, you could reconstitute very quickly. And the backbone routing process was all done independent of the edge devices. It was done by the gateways themselves to discovering their connectivity. So the lesson I learned from this was simplicity is your friend. We didn't specify a lot of the applications that the network would support. And we did that because we didn't know what those applications were going to be. And sometimes incomplete specification is your friend, because the incompleteness gives you flexibility and allows for future expansion. And the Internet protocol itself is a good illustration of exactly this incompleteness. So in the case of the IP protocol, it does not know, each of the packets of the Internet protocol do not know how they're being carried. They have no concept of underlying fiber or radio link or point-to-point laser connection. The packets don't have to know how they're being carried, just like a postcard doesn't know how it's being carried through the postal system. This ignorance meant that when we added new capabilities, such as optical fiber, the protocols at the Internet protocol layer anyway didn't have to change. And that was a big benefit, because you could keep adding new kinds of communications capabilities, just as we did with mobiles and 3G and 4G and 5G and so on, without necessarily changing any of the basic Internet protocol layer. But the second thing that we learned was that it was smart for the packets not to know what they were carrying. And so just like a postcard doesn't know what you wrote on it, an Internet packet is unaware of the semantics of the payload that it's carrying. The reason that turned out to be important is that when someone created a new application that required the interpretation of reinterpretation of the payload, it wasn't necessary to change the network, because the network didn't know what the payload meant anyway. And so only the edges of the net had to change for new applications. And that meant that the Internet could continue to support a wide range of applications and support new ones without itself having to change. Of course, it did change in the sense that we increased capacity and, of course, scale. But other than that, the basic concepts have persisted for all the time that Internet has been in operation since 1983. So this ignorance turned out to be an important lesson. There's a very important other lesson in the architecture of the network, and that's openness. And I found this to be extremely valuable when it came to drawing people into the Internet project and giving them opportunity to exercise their creativity. So at every layer in the multi-layer architecture of the Internet, there is openness to add new features or add new protocols. Now, as you get closer to the IP layer, it gets harder. So all of you are well aware, I'm sure, that IPv4 has been joined now by IPv6, and it's taken many, many years to get very far with IPv6 implementation. Personally, I'm puzzled by this, because almost every edge device, every laptop, every desktop, every pad, every router has IPv6 capability. It's just that the ISPs haven't turned it on. And sometimes they're saying, well, the users aren't asking for it. And my reaction is they shouldn't have to ask. It's the next obvious thing to get enough address space for the incoming wave of Internet of Things and everything else. So although we're about 30% penetrated, I would say that we have still some distance to go. And I'm frankly hoping that the IoT wave will persuade all of the ISPs to simply turn IPv6 on, so we can run v4 and v6 in parallel for a while. But it's taken longer than I would have expected. But at the higher layers in the architecture, it's easy to add new protocols. So for example, The TCP layer, which is what turns IP into a reliable transport mechanism, was joined by UDP, which is a datagram service, which was not reliable, but it was fast. And the reason that turned out to be valuable is that if you were doing radar tracking or if you're doing real-time speech and video, it didn't matter if you lost a few of the packets as much as the delay for retransmission mattered. Human communication is vastly impeded by delay, as any of you will know if you've ever been on a double satellite hop phone call. And so having the UDP protocol there for low latency turned out to be extremely useful. And then there were new protocols for real-time applications. And of course, at the higher layers above TCP and UDP, you got file transfer and electronic mail and the World Wide Web and the hypertext protocols, hypertext transport protocols, and among many others. Which leads me to observe that openness and opportunity for adding new things easily in various layers in the architecture made it an easy sell to get more people involved in participating, because it left them with an open opportunity to try out new ideas in addition to getting the basic infrastructure in place. So that helped a great deal. Looking back on that period of time, I think I also implicitly discovered that as a project manager, the most important thing you had to learn was how to sell your ideas to other people so they would want to do what you need to do. Sort of like the story that Mark Twain told about Tom Sawyer painting the fence and getting his friends to decide they wanted to do that too. So learning to sell your ideas is very important, because if you can't get more people interested in doing what you want to do, it's hard to do anything that scales up. And I think everyone would agree that the internet has scaled up extremely well, but that's because lots and lots of people agreed that they wanted to make it happen. And Bob and I and others were fortunate enough to be able to say yes to them when they needed support in order to do this work. So now we see a multi-layered internet. We also made some other assumptions which turned out to be extremely important. We made no assumptions at all about the business models associated with each of the component networks of the internet. We decided we had no expertise in dictating whether the networks would be commercial or nonprofit or government run or private sector, or we made no assumptions about that. And we said, we actually don't care what the business model is, as long as all the costs get paid for. Because eventually, if you can't pay for all the costs, the system stops working. So we let that be a free variable. Anyone who had a business model that worked was free to participate. We handed out the specs freely on a global scale. We made no restrictions, even though when we were doing this, it was in the middle of the Cold War, and you would have thought, you know, it's a military-sponsored thing. Surely we would want to, you know, contain the details of this design, but we went through a little analysis and realized that we needed to just open this up to everybody. The analysis was interesting. In '73, we said, well, yes, okay, so we're going to design this technology for the Defense Department's command and control system. And then we thought, well, if we have allies, they will need access to the same information, to the same architecture and design. And so we said, okay, so who are our allies at present? That is to say, in 1973. Then we said, who were they 25 years before that? And it was a different list. And then we said, well, who will they be 25 years later? And we said we didn't know. And the consequence of that was we concluded we should just release the design to everybody without, you know, any restrictions at all. And people ask today, how did you get away with that? And the answer is we didn't actually ask for permission. We just did it. And nobody noticed. And the result was the internet design is widely available all around the world, thanks to the Internet Engineering Task Force. Which brings me to one other point, and this has to do with the creation of institutions as the internet has evolved, as the need has become apparent. So when we started out in the ARPANET project, we had this very informal group of graduate students called the Network Working Group. They were from a dozen universities, and they were led by another graduate student and my best friend, Steve Crocker, who eventually also became chairman of ICANN after my term ended. So Steve ran the network working group, and he started the Request for Comment series, the famous RFC series, which continues to this day to be the place where we document the protocols of the internet. When Steve left that group to go on to do his dissertation research, it continued to operate, and as the project increased over time, and I became part of the management team in the Defense Department, we realized that we needed some more coordination as the internet project got bigger. So we set up something called the Internet Configuration Control Board. We made it sound as boring as possible, so nobody wanted to be on it. And I assigned the people who were leading the research in different parts of the research community to be on that configuration control board. And that's how we managed the evolution of the internet protocols. And that group, over time, changed its name from ICCB to the Internet Activities Board, and then the Internet Advisory Board, and then the Internet Architecture Board, which it is today. The Architecture Board was created to have something like 10 task forces associated with different aspects of internet. And eventually, one of those task forces became the largest of them. It was the Internet Engineering Task Force. And so we took all the others and we lumped them together into what we call the Internet Research Task Force. So now there are just those two big task forces that are part of the standardization and exploration structure. Other institutions that got created at need, again, I would include among those the Internet Society, which Bob Kahn and I and others started in 1992, because we needed a place where the Internet Engineering Task Force and the Internet Architecture Board could be formally housed. We also needed a place that could support their operation financially, because the government source of support, in this case the National Science Foundation and DARPA in particular, were unwilling to keep spending money on what had become an increasingly commercial activity. So the Internet Society got started as a nonprofit, and of course it persists today. Later, as the management of the domain name system and the internet address allocation process grew, again, institutions were created, 5 of them called regional internet registries. Aaron here in North America, the Americas Registry for Internet Numbers, LACNIC in the South, AFRINIC in Africa. There's a group in RIPE NCC in Europe and APNIC in the Asia-Pac region. These 5 regional internet registries manage the allocation and assignment of internet address space. And the Internet Corporation for Assigned Names and Numbers was created in 1998 to manage the domain name system, oversee its functionality, and also the allocation of IP addresses to the regional internet registries. So I'm actually very proud of the fact that the technology has been accompanied by an institutional willingness to create institutions to serve a certain need. So some of you will know that there was a World Summit on the Information Society sponsored by the United Nations in 2003 and 2005. And coming out of that World Summit was an Internet Governance Forum, which still meets every year to discuss issues arising with regard to the governance of the Internet. And that itself, this international thing, spawned additional activities at the national and regional level. And so the lesson that I learned out of all of this rather lengthy history, is that institutions should be created when it's clear they're needed to fulfill a particular function, and not to invent them, just for the sake of inventing them. And I think that it has served the internet well to have these institutions created as the need for them has persisted. So coming back now to lessons, I think that perhaps the most important lesson that I can share with you in terms of project management and even in the connection with startups is that starting with small groups really helps a lot. 5 or 6 people are amazingly agile. If they are able to stay in touch with each other, it's a challenge in today's COVID world, but if they can stay in touch with each other and they have high respect for each other, there's really not much limit to what you can imagine. I worked on a number of projects, including the interplanetary extension of the internet, which started with just a half a dozen people. And the value of that small group beginning is that if everyone recognizes the same objective, we all know where we're going or what it is we're trying to do. Maybe we don't know how to get there, but if you have a good idea about what it is you're trying to do that's easily stated, then, and if you have respect for each other, which is really important, then while you're trying to figure out how to get to the target, you may have disagreements. Engineers frequently disagree with each other about what's the right way to do something. But if you are respectful of each other's opinions and recognize that you're all trying to get to the same place, then you can have those debates and evaluate the options in a, it may be passionate, it may not be a dispassionate evaluation, but at least it's an evaluation which is based on, real data and hard metrics and respect for each other's opinions, as opposed to telling somebody you're an idiot because you think X, Y, or Z. And so this small group phenomenon, high respect, and easily stated goals can be super helpful in making progress. So to give you a very concrete example of that, in America, many of you will remember in 1963 that President John F. Kennedy said that he thought the America should commit itself to sending a man to the moon and bringing him back successfully before the end of the decade. Now, that's a very easily stated objective. Everyone could understand what that was intended to achieve. And so you could ask yourself, if you were part of that project, as I was back in the 1960s, is what I am doing contributing to the objective? And with a simply stated objective, it was often pretty easy to figure out whether what you were doing contributed to it. And if it didn't, you might ask yourself, why am I doing this? So this easily stated objective is extremely helpful. At Google, our motto is organize the world's information and make it universally useful and accessible. And, that's an easily stated goal. It's an incredibly hard problem. We have 100,000 people working on that problem. And it's helpful to have such a simple statement of goal in order to test whether or not you're contributing to it. And so if you can characterize the project that you're doing or the company that you're trying to start with a simply stated goal, it will help all of the employees figure out whether or not what they're doing is contributing to the destination or getting you to the destination. So I have a suggestion that you probably have questions to ask, and I can tell that you popped in to do that. So why don't I stop there and invite questions?
Well, thank you so much for a great presentation. Would you mind taking a minute to summarize the pearls of wisdom that you shared with me in our pre-call, one professional and one personal? I thought the stories were incredible.
So you have to remind me what those were, because I don't remember. Do you remember what they were?
Yes, the professional one was about patience and persistence.
Oh, yes. Okay, thank you. So you're quite right. The other thing which I hinted at in my discussion is that patience and persistence really count. All the projects I've ever worked on have taken a great deal of patience and a great deal of persistence. And I'm amazed at how much you can do if you're willing to allow it to take time to get to the destination, to deal with false starts and things like that. So yes, that was one. And the second one, I do remember now. Second one is that you can learn something from everyone. And I learned to be very thoughtful not only about that, but also not to make any assumptions about anyone, especially someone that I had just met. And I illustrated this point with a story in my youth when I was being driven in a limousine to go give a talk in California in Palm Springs. And I was younger then, and I had dark hair. And I noticed that my driver was this old guy with white hair. And I'm thinking, oh, this is so sad. This poor guy is still working, while he's old, and he's in Palm Springs. He should be just out there on the golf course, relaxing and retiring and enjoying life. Well, so I made the assumption that his was going to be a sad story. Well, it turned out in conversation that he was one of the CFOs at one of the largest insurance companies in Chicago. He had moved to Palm Springs because he was planning to retire and play golf. But after 6 months of playing golf, he decided he was bored. And so he took a job driving a limousine 3 nights a week because he knew he was going to meet interesting people, because those were the kind of people who could afford to take the limousines. So I learned a lesson from that one is don't make any assumptions. And second, you can definitely learn something from anyone you meet because they've had experiences you haven't had. And you can take advantage of that by not having to have their experiences, but to experience them vicariously. So thank you for the prompting. I appreciate it.
No worries. Thank you. So Ray, who introduced us, thanks you for a great presentation. And he has a question as well. Will other countries like Russia, China, or EU be able to build a new or different internet?
Well, they're certainly trying to distort the original intent of the internet, which was openness and the ability of any device to communicate with any other device, for any person to get access to any other device. We didn't put any limitations because in the early design, we weren't sure who needed to talk to whom and for what purpose. I still believe that flexibility is important. But there are, as everyone will agree, I think, we've seen what happens when you open up the world to this kind of communication. And we particularly see that people are people and they do things that are often harmful to other people. And using the internet as the medium through which to visit that harm, whether it's malware or distributed denial of service attacks or misinformation and disinformation or bullying, all the other things that we see, unfortunately, in social media, for example. So the question is what to do about that. And in some cases, regimes will decide that the way to do that is to regulate highly and to control who has access to what information and to block access to some information. In other societies that are more democratic, there's a stronger desire to keep things open. But there's still going to be a persistent expectation that protection of people from harm in the online environment has to be achieved somehow. And so we are in the midst of a struggle to figure out what's the right way forward to maximize the value of this online, global, and still very open resource, and at the same time protect people from harm. There are some regimes that have a definition of harm which may not necessarily be the same as yours and mine. One definition of harm might be the population is free to talk about the regime and they don't like us, and so they want to change the regime, and some regimes don't want to be changed, and so they will do everything they can using this resource in order to prevent people from achieving that objective. So you get heavy surveillance, you get all kinds of other blocking and filtering and a variety of other behaviors. And to be honest, I think an example of that is found in China, where they invested very heavily in internet. They have huge companies like Alibaba and others. And so they've been very successful with the technology, but they've also decided that they want to control and limit access to information to the Chinese population. That's their response to the definition of harm. So I'm expecting that the net will continue to experience pressures to fragment because of that. And my honest hope is that in spite of those pressures, we will somehow be able to keep the internet as open as possible to take advantage of all of the utility that freedom offers. But I also accept that we're going to have to do something about the harmful things that happen in the net, whether it's literally doing some form of regulation or at least teaching people how to be safe in the online environment if they are not adequately protected. They need two-factor authentication. They may need strong authentication. They may need cryptography in order to protect their traffic. You know, a variety of technical things that we can do in order to keep the internet as useful as possible. But I do think that we are going to experience some fragmentation, whether we like it or not.
The two follow-on questions, and if you've already addressed it, we'll skip to the next one. Looking back, would you have done anything differently with regards to security? And what's your take on the Great Firewall of China?
So I think we've responded on the Great Firewall. With regard to doing something different, there are two things in particular that have been a challenge. As everyone knows, getting IPv6 in place, as I mentioned earlier, has been tough. I suppose if we had started with 128-bit address space, we wouldn't have to go through this transition. But I ask you to imagine in 1973, why would anyone believe that you needed 3.4 times 10 to the 38th addresses to try out a system that it wasn't clear was going to work in the first place? And oh, by the way, the 32-bit address space allowed you to address 4.3 billion terminations, which is more than there were people in the world at the time. And so it seemed to me that the 32-bit choice was reasonable, and that if the internet demonstrated success, that we could do a production version of it after the success had been demonstrated. Well, I would argue IPv6 is the production version of the net. And we need to get with it, just get going, get this over with. The second thing, obviously, has to do with security, safety, cryptography, and the like. Key distribution is a real difficult problem, except for the arrival of public key crypto, which allows key distribution to be done in a very flexible way. Public key crypto was an idea in 1976. It was published by two of my colleagues, Whit Diffie and Marty Hellman. They hadn't actually implemented anything at the time, and about that time frame, 76 to 78, I was freezing the internet protocols as the program manager at ARPA in order to get the system implemented so we could see if it would work. So during the same period when public key crypto was evolving, the internet is starting to go into its primary implementation phase. And so I didn't think that I could push all of that into the system without delaying our ability to find out if it was going to work at all. On top of that, it's fair to say that most of the people who were helping to build the internet in its early stages were graduate students at universities. And I would challenge you to argue successfully that key management and key utilization would be a strong point for most graduate students who are distracted by classwork, final exams, and their dissertations. And so I did not push that very hard, knowing and believing that we could retrofit that, which we have done in the net. And so you're seeing a substantial amount of cryptography and digital signatures and strong authentication methods showing up in the network because they are, in fact, retrofittable.
Thank you very much. So I realize you have to leave. You have another appointment at 1:50. So I'll go ahead and ask the last two questions so that you could combine them too. So we have one comment, which is the internet is a great tool for good, but it's become a source for hate speech and malicious information. How do you think internet content can be better managed or monitored? That is question one. And finally, to wrap up, what do you think the internet will look like in 20 years?
Okay, so on the first question, it's clear that there are some technical things that we can do to protect against the harmful behaviors that we see on the net. And so where it's possible to do that, that's often preferable. So discovering a denial of service attack or detecting malware and things like that could be not perfectly done, but can be done with technical means. That's not going to solve all the problem, though. And so we also have to say, okay, we will need to adopt some norms, certainly nationally, if not internationally, and say that if there are certain behaviors that are unacceptable in our society, if we catch you doing them, then there will be consequences. This is what we'll call post hoc enforcement, where you essentially apply the law after you discover someone has broken it. And that doesn't work perfectly either, because not everybody who breaks the law is discovered, but at least you're on notice. The third thing that you can do is to say to people, just don't do that because it's wrong. And that sounds weak, but I have to remind you that just as gravity is the weakest force in the universe, but with enough mass, it's very powerful. It keeps the Earth in orbit, for example. That social norms can be very, very powerful in the way in which society behaves. And so we need to adopt social norms that reduce the level of incidence of some of these harmful behaviors. The last point I would make is that we can also make use of the wetware up here to evaluate the data that or information that we get, and ask critical questions. Where did it come from? You know, what's its origin? Is there any corroborating evidence for assertions that are being made? Do we know who is supplying this information? Does that give them credibility or not? So there are a variety of questions that humans can ask themselves before they are taken in by misinformation and disinformation. That takes work. And so we need to train people early how to do it in an effective way, children and adults. And once we get into the habit of asking critical questions of the information that we get, the less impact, I think, some of these harmful behaviors will have.
And the final question, what do you think the internet will look like in 20 years?
In 20 years, right. So first of all, the interplanetary extension of the net will be in operation by that time. We're already part of the way there with prototypes on Mars and Earth and the International Space Station, and the moon missions are coming up. We will be expanding internet operation to those places as well, using a new suite of protocols that are more flexible than the TCP/IP protocols when it comes to variable delay and disruption. So over a 20-year period, I am confident that we will see that expansion happen. The second thing is that bandwidths will have become, substantially larger, and we won't be. I don't think we'll be very worried about bandwidth in 10 or 20 years. Virtually everybody will have access to gigabit speed capability at reasonable costs. Of course, I can predict that, but somebody has to make it so. That means we have to deliberately decide to make investments to make that future happen. I think the third thing is that the Internet of Things will be everywhere, and we won't pay much attention to them because they'll simply be doing what they're supposed to do until they don't, which is the great difficulty with any kind of infrastructure. You ignore it until it doesn't work, and then when it doesn't work, all hell breaks loose. So we will probably have incidents in the 10 to 20 year time frame where the infrastructure that we're relying on doesn't work as well as we would like it to. And there'll be a big hue and cry about that. But we've worked our way through all this before, and we can do it again.
Well, thank you again. I think you had enough reminders to tell you when your next appointment is. So thanks again for joining us and giving us your valuable time. And TiE Pittsburgh and the community thanks you for taking actually all our questions and sharing your wisdom with us. Thank you so much.
Well, it might not be wisdom, but it was free advice, and it might be worth that much. But I'm happy to have had the opportunity. Thank you very much. Good luck to TiE and all of you.
Thank you. Prashant, you want to say?
Thank you. Thank you, Dr. Cerf, and thank you everybody for joining us today, and we'll look forward to seeing you on the next event. Thank you.
Indeed.
Thank you, Vint. Thank
See you
you.
on
Thanks, everybody.
Thank you very much.
Thank you, Ray,
Thank
also.
you.
Have a good afternoon.
Have a
Bye-bye.
great afternoon.
Bye.
Thank you, everybody. Thank you.